Great. Well, thank you all for staying late and coming to my talk this afternoon. So I'm going to talk about data science with OpenShift and how that can kind of help data scientists in their day-to-day work. So there's already a little introduction about me, but as you said, my name is Michael Clifford. I work out of the Boston office in the US, working on the AI ops, and that's really trying to build these like intelligent applications to support IT operations, particularly operations like around for cloud applications, like specifically those that run on OpenShift. And luckily for me, a lot of the work we do at Red Hat is open source software. And so a lot of the work that I do can just be found readily on GitHub at Michael Clifford if you guys want to reach out to me there after the talk or see some of the other work we're doing. So great, what am I going to talk about today? First, talk a little bit about the Red Hat AI COE, which is the company, the kind of division that I work in. And then we'll talk about, if we want to talk about data science with OpenShift, talk a little bit about what OpenShift is and then kind of what data scientists do to connect those two topics. And then we'll talk about some of the current challenges that exist for data scientists who are trying to work into this more like cloud native environment. And then finally, I'll discuss a tool, or like it's a really great entry point for data scientists who might not be that familiar with using containers to kind of work on reproducible portable notebooks. And we'll be using something called notebook to image. And then I'll walk you guys through a demo of how that works. So the first thing I want to do is just kind of lay some groundwork about how Red Hat sees AI. And so we see it kind of existing in these four broad pillars, which generally I would say cover many of the obvious topics that a software engineering company would want to do. So first we have like AI as a workload, and that's really just thinking about the actual computation that goes into running AI. You have GPUs, a lot of resources that go into running these kinds of things. So we want to make sure that both our platforms, specifically RHEL and OpenShift, are like well suited to do that. And so it means that like we really want to have that proper hardware enablement, like library optimizations and the core fundamentals for hosting and optimizing AI workloads. And then again, like Red Hat, like any other business, wants to take advantage of the kind of the progress that's being made with AI. So we also look at how we can help like the business side of Red Hat to incorporate some more intelligence into their kind of sales operations and that part of stuff. And then again, the part that I primarily work on is this third pillar, where it's about building intelligent applications and like AI-powered products and services. So here's things like doing anomaly detection in telemetry data, or doing like log anomaly detection for different applications, and different things that essentially make the running of our cloud platform more intelligent. And then the fourth pillar is really about how we can make sure that our platforms are set up in such a way that it really enables our customers to build their own intelligent applications on top of our services. And that's kind of mainly what this talk is going to be about today, that piece of it. And then finally, obviously, we have data as the foundation. That's kind of like the new oil or whatever it is that's really important for all of these data science applications to work. But there's really like a more philosophical element to it, right? So as Red Hat is kind of we see ourselves as the leader in open source software and just open in general, as we're now transitioning from a kind of a technological state where software just in and of itself is like insufficient to get the reproducible results. You still have to have, in often cases, like the trained model and the data. So how do we help foster that transition from just pure code to data and code as the foundation for these intelligent applications? I think that's still definitely like a bit of an outstanding question, but it's something we're working on. So cool. So that's just quick stuff. But yeah, so if we're going to talk about data science with OpenShift, let's first talk a little bit about OpenShift. So how many people here have heard of OpenShift before? Okay, a lot of people. Good. Maybe that's why you came to the talk. I'm sure you've all heard of Kubernetes as well. Yep. Cool. So yeah, just I was expecting fewer people to know about OpenShift. But yeah, I mean, basically it's just a container orchestration platform that allows us to more easily kind of like manage applications, both machine learning applications and like traditional ones across the hybrid cloud. So as we've moved away from these like singular monolithic applications and transitioned to a more microservice paradigm, like we developed huge gains in flexibility, but it came at the cost of complexity management. And that's like exactly the problem that both Kubernetes and by extension OpenShift are here to solve. And just to be super clear about it, OpenShift is Red Hat's distribution, like enterprise distribution of Kubernetes. So that's all to say, it allows us to like really easily compose, deploy, and manage cloud-based applications, but as long as we use like containers as the basic building block of our application. And this graph here is just to show, you know, that OpenShift can really run across any platform, whether it's your local laptop, Amazon, AWS, Google Cloud, whatever, it can run on these platforms, and then it gets exposed as this set of microservices that work together to generate an application. Great. So now that we have a reference for kind of what OpenShift is, I want to talk a little bit about data scientists and what they actually do. Sorry, oops. So it's the end of the DataSphere conference here, and I'm sure you've all seen some version of this graph a few times already. But just want to give you like a high level idea of what the data scientist workflow looks like. So how many people here are data scientists? One? Okay. All right, great. So in my opinion, I would say like the data scientist is really a software engineer whose primary responsibility is ensuring that the machine learning project that we've been tasked with is performing as expected, so that it's getting the right, whatever the intended output is, whether it's image recognition or some kind of classification task. It's our job from a technical standpoint to ensure that it's actually getting the results that the business or the project needs. And that whole kind of workflow is somewhat outlined by this graphic here. And so we're usually given some high-level description of a business or a research problem. Like, we want our customers to get better recommendations about whether or not they should replace a given hard drive. And that's like not really like a well-defined problem from a technical sense, maybe. So we try to like codify these requests into like machine learning problem, right? So like, can we actually extract and encode the operating signals produced by a hard drive in such a way that we can accurately predict the time to failure, and maybe we can use a regression model to solve this problem. And so this is all like existing in that very first blue bucket. And then hopefully we're like provided with a really clean data set that's well suited to start answering this question. But in practice, that's simply not the case. So there's a lot of time that goes into figuring out what data is actually needed to solve this problem, and then cleaning the data and formatting it in a way that's reasonable to start working with. And then we go through like the exciting part of feature engineering, model training, and model validation. And this is really like an exploratory process. And it's quite iterative. And perform experiments until we feel that our model performs sufficiently well within our validation data, like given our specific business requirements. And this is all like, from a data science perspective, a lot of this is done through like Jupyter Notebook environment. That's a very popular environment for data scientists right now. And then we want our model to like actually be used by somebody, right? We want it to be useful. So we want to deploy our model. And we want it to be a service that people are using. We also want to have some monitoring that we can use to validate that it's actually working in practice, and maybe there's data drift or some other something is occurring that we can see in the wild is not performing correctly, and we can go and we can address that, and then we can kind of go back to this middle chunk here and try to perfect it. So yeah, so I would say that kind of like sums up in a nutshell what the data scientist day-to-day workflow looks like. But what are some of the challenges that data scientists face today, right? Like, what are some of the problems that aren't immediately obvious from this workflow here? So the three main issues, I think, kind of fall under this notion of collaboration, infrastructure, and time to value. So when it comes to collaboration, I see none of you are actually data scientists here. But if you are, has a data scientist ever like sent you a notebook and said like, oh, run my notebook and see how well it works? Is that hand raised? Has that ever happened to anyone? Okay. Well, I can assure you that I've done it, and it typically does not work very well. Usually you get something like, oh, yeah, you have to have a specific version of a package for it to work, or, oh, I forgot your machine doesn't have GPUs, or the data directory has to be changed in some way. So then this is when you're working among other data science colleagues, and it's just a hassle that like shouldn't really have to exist. So sharing reproducible notebooks is a big issue. And then that's, like I said, that's between two data scientists, right? And the problem, I think, it's even worse when you're working just with like a software engineer who's maybe like less familiar with your workflow, and they're just trying to go ahead and kind of port your model into a larger application. The kind of the iterative, agile working process can become a lot more sticky in that case. Yeah, and then when it comes to infrastructure, right, like you can't do everything on your laptops. You might need like GPUs or Spark clusters or any other specialized hardware or expensive computing procedures. So, right, like companies don't want to buy huge deep learning machines for each of their data scientists. We want to be able to also take advantage of that like core principle of elastic computing and kind of share the resources that we have available across our teams. And then something that I think is like the most important is this issue of time to value. I think a lot of times data science projects can kind of get stuck in limbo in a notebook, just some data scientists infinitely iterating to get 99% instead of 98% accuracy. But even still, like I think we're slowly moving away from this paradigm. But in the past, a common workflow has really been for data scientists to be given some problem, they work on it in a notebook for like n amount of weeks, save their model, and then it gets handed off to a software engineer, and then they build and deploy this application. And like I said earlier, with the collaboration piece, I mean, it's quite slow, and I think it would be great if there was a way that we could really like speed up the process, or like kind of shorten that distance between a notebook proof of concept and a deployed prototype. So these are like somewhat inscrutable issues for data scientists right now, especially I think in the enterprise space. I know that there are, there's definitely some tools out there to address some of these individual issues. But as far as like that open source enterprise space, there's not really a good solution to that. So yeah, what I would like to argue for the rest of this talk really is that a containerized approach to data scientists, and more specifically using OpenShift, can help alleviate some of these issues. So, right, how can containers help and OpenShift help me, a data scientist, solve some of these problems? So as far as collaboration, right, notebooks can become far more portable and reproducible if we run them as containers. Team of developer, so you can send an image of your notebook to another developer, and it's like guaranteed to run on any platform, because that's kind of the base kind of sales point of what images are good for. Or if you can even using a platform like OpenShift, right? You could host your image. You could host your image, but you could also host your notebook as a service that somebody could actually go to and see the notebook, run it themselves. So there's not even a concern about what their environment is like, right? You could just directly point them to some hosted environment where your notebook's running, and it will have the same results. And then when it comes to infrastructure, right, like you're no longer bound to the CPU and memory limits of your laptop. You can get access to the more powerful shared resources that maybe your company provides. And then that time to value piece, right? So like developing a machine learning code that already runs as a container image, it can super easily be plugged in to a larger application and quickly deployed as a service. I mean, it's already kind of the native base unit of these microservice infrastructure. So if your model also exists in that way, it just seamlessly falls into the kind of cloud native architecture. And I think that really shortens that gap between notebook proof of concept and a deployed prototype. So like, what's one way that we can take advantage of containers and OpenShift to quickly deploy and share our machine learning work, right? Like what's one thing that you guys can take away from this talk here today? So I'm going to walk you through this tool that was developed by a colleague of mine, Will Benton. It's called Notebook to Image. And here's like the Quay.io repo to get access to this image builder. And this is already something, so there's already something that's part of OpenShift called S2I, or source to image. And it's a really nice tool to be able to basically, if you have code stored in a Git repo somewhere, you can just point your S2I builder to it. It downloads the repo, runs the code, and stores it as an image that can be deployed as a container. And this application, this specific builder essentially does the exact same thing, but it's specifically designed for notebooks. So a data scientist doesn't need to learn about Docker files or do anything tricky. They can just stay kind of in their comfortable notebook environment and go directly to a deployed application to maybe get feedback from a customer or their team. Yeah, so I'm not going to like lie to anyone here, right? It's a little bit more complicated than just opening your notebook, importing like sklearn, and you're off to the races. But I think that if you really want, if your final goal is to develop a machine learning tool that can be used by others, taking some of these extra steps to do data science with like a cloud native mindset from the get-go can really pay off. So great. The next thing that I'm going to do is walk you through an OpenShift console and an application that I deployed a little bit ahead of time, and just only because I don't want you guys to sit through a bunch of things loading. And I can show you how to kind of configure and manage it to work with Jupyter notebooks, Ceph storage that we have, that is a shared Ceph storage used by our team, and then how to use this S2I builder specifically for notebooks. And they will be deployed as an application. They'll have like a REST endpoint, so it can actually be, you can query it for inference. And so besides a few command line instructions, like the bulk of the code just going to be written directly into a Jupyter notebook. We'll also be able to like edit our notebook, push it back up to GitHub, and deploy a new model without like any downtime of our application. So again, I just want to like reiterate, like, why would somebody want to do this? Like, none of you guys are really data scientists here, it sounds like. So what would be the point of doing these things? And I've said this a couple times, but I think it's really important. Like, this really closes that gap between a proof of concept that's written in a notebook by your data scientist to a deployed application, which you can show like a real demo basically to your end user or your team or whoever's going to give you feedback. So you can kind of get that iterative process going a lot quicker and shorten that time to value. Also, packaging images as notebooks just makes them so much more portable and so much more reproducible. And again, having models being able to be, even when you're into production, having models deployed as images on OpenShift makes it so there's like no downtime of your application of your model. Cool. So I'm going to jump into a demo here quickly. Just need to change the screen. All right. So what you're seeing here is, can you guys read that at all? No? Let me see. Is that better? Okay, great. Yeah, so this is an OpenShift console that you can interact with to kind of manage your application. So I have two applications deployed right now. I have Jupyterhub, which I'm going to use as the Jupyter server to interact with my notebooks. And then I have the model that I deployed ahead of time, but I'll show you how to do that. It's quite simple. But so you can just go to this route here, and we'll spawn a Jupyter notebook terminal for you. This is also extremely small. Okay. Yeah, so is anyone here familiar with Jupyter? Have they ever seen it before? Yeah? Okay, great. Cool. So yeah, so this is just your standard Jupyter terminal. But so, right, if you are on OpenShift, this is actually running in a server center somewhere on top of your like optimized hardware. So it's not necessarily just running on your machine bound to the limits of what you have locally. And then we have a notebook here that I'll just walk you through quickly about how you'd actually go about setting up a notebook to deploy it on OpenShift. So this is going to be giving you access to OpenShift, installing the OSI Client, git cloning a repo that you want to be reproducible. Maybe it's your friend's repo or your own that you want to try out, how to deploy it as an application, expose it as a service, and then actually interact with that service. So the first thing here to note, so if you guys actually want to like try this yourself after the talk, you can just go to okd.io. This is going to be small maybe. And it has a really good guide for just like getting started, and you can deploy this. It doesn't need to be on a server or anything like that. It can even run locally on your machine if you want to test it out. That's what I'm doing here for this demo. And then you can just go ahead and install the OSI Client. That takes a little bit of time, so I did that ahead of time. And then you can log into your OpenShift cluster. You can see that I'm the developer. I'm working on this project, my project. And it's probably quite obvious to you guys that so this is my project, developer. This is interacting with the same OpenShift cluster that this dashboard is presenting. There's just a lot of times where it's much easier to do things from the command line and do it directly. Also, this is being done in a notebook now, but it's really just to kind of record the process. This can be done directly in a terminal, no problem. You can also clone this from my repo later if you want to go through it yourself. Yeah, and then we have some notebook, right, that we want to actually turn into an image. And I've already downloaded it, so it's not going to download again. But we can jump over into this repository where we have something called model. Yeah, so if you want, so there are some conventions that need to be set in order to get something to automatically go from a notebook to an image in a deployed model. It's not a ton, but it's worth considering. Because what the image builder does is it does some post-processing of like the code of the notebook. So it requires just a few things so it knows how to build the image correctly. So you just define like the requirements like you would, and it builds a text requirements.txt file for you from this like list of strings of the different requirements you need. And then you have your model code, and when you're working with notebooks, you can do kind of wonky things and run cells out of order, and they will still work. But because of the way that this is how this will work eventually when it gets post-processed, it rips all of the Python code out and puts it into a script for you. So it just requires that all the cells run in series without issue. And then we can use OpenShift. So let's say you want to share data with some team and you have some shared Ceph bucket that has the data that you want to get access to, right? So you want to define these environment variables with the keys and secrets. And OpenShift allows you to kind of set these inside of your terminal so that I can kind of show this will work, but those keys aren't actually being exposed to anyone. And both when I'm working in my notebook and when I actually build the image, it's going to like call to that same Ceph bucket and process that data for us. And then the super exciting part here, this extremely intense data science work we've done here, which is basically just doing a random forest classifier on about 1,000 lines of code, of data. And again, it's not really anything fancy at all, it's just kind of selected for speed, for purpose of the demo. But the main takeaway here is that it doesn't matter what I put here. I could change this to a TensorFlow model, PyTorch, like any much more complicated data processing, data cleaning, like computationally intensive model. If it runs in your notebook and you define the requirements correctly, it will run and be deployed as a model here. And then the other two things that you need to have set up for this to work is to have something called a predictor and a validator. And really the predictor is just like that inference step that the REST API will call to and generate predictions for you. And then the validator is there simply to kind of handle errors in your code. So if somebody sends you code that's just not, or if somebody sends you an input that's not valid, it will catch that. So in order to, so this is really like straightforward, I think. Like, so as somebody who, if you're doing data science, you want to kind of get into containers, maybe it's like a little intimidating how to figure it out, how to actually get your model deployed. By just like formatting your notebook in this way, with just, I think there's like 3 different requirements, it can super easily just be deployed and can get feedback quickly. And the way that you do that is if you go back to this notebook here. So yeah, it's really just one line of, can you see this? One line of code. So you use the OSI client that we downloaded earlier, define a new app, give it a name, and then call this quay.io Will Benton simple model S2I builder, and as a parameter, just point it to the notebook and the Git repository where the notebook's stored, and you're good to go. I'm going to call this something too, since I already have one loaded. Great. So yeah, so it found the image, it's pulling it down, going to build it, creates all the resources for us that would be needed. So the image stream, build configurations, everything to deploy the model. The only thing that it doesn't do for us is actually expose it, expose the service route, but it gives you a warning to do that, so it's quite straightforward. We can just do that here. Great, so now you'll see in your console that we have a second application that's been deployed, and it is building. We can look at the logs. It's basically downloading this repository and doing all the stuff that it needs to do to run and train the model. Great, and so we've done all the hard work, and we actually want to interact with our model. We want to make sure that it's actually being served and that people are able to interact with it. And to do this, I mean, you could use any kind of tool that allows you to interact with REST points. I'm just going to use the requests in Python because it's quite simple. But you just define the routes that we exposed here, and you can do that. And we know, right, so we know that the input to our model is a 29 length vector, so I've just given it some dummy input as 29 ones, and we're going to interact with that point, and great, we got a prediction, class 0. Given like the simplicity of the model, I'm not sure how accurate that is, but again, like if we give it something inaccurate, like 39 ones, that validator function comes into play, and it kind of responds that this is not appropriate data for us to use. Great, so what if I actually want to change my model in some way? This is like insufficient for what I want to do. So, whoops. I can go here, make whatever changes I want, as long as they fall within that necessary requirements. And from OpenShift, we can just go into builds, and you can see I had some issues this morning trying to get it to work, and kick off starting a new build. And so this will it's going to be the same code again, but if you had uploaded a new model to GitHub or a new code, it would bring in that new code and retrain the model, and then serve it. And while that's happening, it's all kind of happening on the back end, and the pod that's currently serving the existing model doesn't go down. It's still up and serving. So we can still interact with it while the model is being updated. And if for whatever reason it breaks or goes down, or your model build doesn't work, it doesn't change anything. It just stops the build and keeps going, or it keeps this model alive. Great, so I think that's basically all I wanted to share with you guys today. So yeah, thank you.
Thanks a lot, Michael. Again, like with the previous presentations, I think we'll go with the live questions. We can. Oh, don't forget to rate the talk. Obviously, there is actually one question here. How does it? Yeah.
Sorry. Yeah. How does it compare to Google Colab? I'd say it's quite different. Google Colab is nice for sharing, but I'm not so can you deploy models like directly as containers in Google Colab? I mean, I think Google Colab is quite good for sharing, but as far as making it like a interactable service, I'm not sure if Google Colab fulfills that need, or if it can kind of package it as an image that can then be integrated quickly into a wider like microservice architecture. But I could be wrong about that.
Yeah, good. I'll give you the mic.
Sorry?
So I wanted to ask about auto-scaling. So when you deploy it in Kubernetes, so OpenShift, does it actually auto-scale on many machines? Do you configure it somehow, or?
Yes, so OpenShift allows you to have like auto-scaling in place, I believe. But this particular deployment would have manual scaling. So you know, I could create. I could just go in here to my Jupyterhub and this might crash my computer, but I just like deploy a second pod. And then as far as having like an auto scaling, there's definitely like thresholds and configurations that can be set such that, you know, if CPU usage starts to get to some point, automatically deploy another pod for this particular application.
Okay, and another question is about the versioning of the models. So let's say you make a change to a notebook, and you know, you make, I don't know, 5 changes, and you have 5 models, and then you have, you know, 10 different notebooks. It becomes a little bit of a mess, I guess, with all those things.
Yeah, so 2 things there. One, if you're using GitHub as kind of the repository for where you're deploying, like as you're doing like source to image or notebook to image, with GitHub being like the repository that you're pulling from, you're doing that versioning there. You also have, it retains the different models that you've deployed. I'm not sure if it would remember that the GitHub source code has changed, but there is some versioning of the actual models as they're being built here. Like you can see that's built this 8 times in the last couple of days. So there's some ability to go back and see what performed well and what didn't.
Okay, so it does manage it somehow, makes it easier to keep track.
Yep.
Okay.
I've seen there's actually another question on Slido about more complex models and performance. If you could maybe make it bigger, can you?
Yeah, sure.
So have you been testing it with more complex models? What about performance? You can do some stuff with Dockerfile to run it faster or slower.
Yeah, so I mean, like I said earlier, it's as far as the complexity of the model is, I think, kind of irrelevant for this particular tool. As far as performance it would take, again, I think that this tool is really designed for kind of data scientists who are looking to get that first step into how they can containerize and deploy their notebooks. So it's not super concerned about whether it's more performant than just running it as a Docker file.
Okay, thank you.